I want you to picture something. It's very simple. 2 apples on a table.
Okay.
You add 2 more. You count them. 1, 2, 3, 4. It's the most basic truth we have.
Yeah.
2 plus 2 is 4. It's bedrock.
It's the one thing that feels absolute safe.
Exactly. But then I'm reading through this stack of research you sent on AI crystal computation, and I had this moment where the floor just dropped out from under me.
It's a bit of a vertigo moment, isn't it?
It is, because the source material asks this question that sounds, frankly, insane at first. What if 2 plus 2 isn't a constant? What if the answer depends on the shape of the universe you're counting in?
And that's where you realize the ground might not be as solid as you thought.
Right. And we're not talking about, philosophy here. This is a proposal to invent a brand new mathematical operator, a way of doing math that it completely rewrites the rules.
That's right. And we're looking at a synthesis of 2 really huge frameworks. You've got AI crystal computation on one side, and this other thing called Conditional Algebra Expansion, or CCT. And the mission for this deep dive is to see if we can actually build that new math by combining them.
Okay, Conditional Algebra Expansion. That sounds like the name of a class I would drop on day 1, so let's unpack that. My read on it is that the symbols, the plus signs, the equal signs, they stay put, but their meaning changes. It collapses.
That's a perfect way to put it. Think of the plus sign like a chameleon. It looks the same, but depending on the background, the filter you put behind it, it changes its function.
So in our normal flat world, the plus sign is just plus. But if you put a crystal filter behind it, suddenly that plus sign has to obey a new set of rules, the rules of that crystal.
Precisely. And that's what we're going to try to do, build this new operator. But to do that, we have to start with the core concept in the source, which is this idea of angle complexity.
Yeah, I got stuck on that too. I hear angle, I think of a protractor, 90 degrees. What is angle complexity?
It's so much more than that. I mean, we're not talking about a simple corner. In this framework, space isn't empty. It has a structure, like a crystal. So angle complexity is, well, the technical term is the multi-scale entropy of directional symmetries.
Okay, you definitely lost me at multi-scale entropy. Break that down.
But, fair enough. Let's visualize it. Imagine you're in a room tiled with perfect squares. The corners are all the same. Predictable. Low complexity.
Got it.
Now, imagine you're inside a fractal, like a cos snowflake.
Those patterns that just keep repeating as you zoom in?
Yes. And if you look at a corner and you zoom in, the line isn't straight. It breaks into a jagged pattern. Zoom again, and those jags have their own jags.
Ah, I see.
Angle complexity is measuring that. It's not just one angle. It's the whole history of all the turns and branches as you go deeper and deeper.
So it's like a coastline from space looks smooth, low complexity. But if I'm walking on the beach, I see all the rocks and inlets.
Exactly.
And if I'm an ant on a pebble, it's a mountain range.
That is the perfect analogy. And that's the key. If we want to add numbers in a universe like this, we can't use a straight line. Because straight lines don't really exist, we have to use that branching, jagged structure.
Which brings us to the star of the show, this new symbol, the Angular Fractal Sum.
Or the crystal path fusion operator, if you want to be formal.
And the notation for it is pretty cool. It's a plus sign inside a box with a little theta subscript.
Box plus theta. And that little theta is everything.
That's the crystal filter. It tells you which universe's rules you're playing by.
Exactly.
Okay, so let's use it. Let's say I have 2 numbers, 5 and 3. Normally I just get 8. But with this box plus thing, what actually happens to my 5 and 3?
Well, first you have to completely abandon the idea that numbers are just static quantities. In this system, a number is a path.
A path, like on a map.
A sequence of vectors. This is step 1. The fractal encoding map. You embed the number 5 into that infinite angular tree we talked about. So 5 isn't a magnitude, it becomes a set of instructions. Go forward, turn 60 degrees, go forward again.
Wow. So a number is a journey. It's the story of how you got there.
A story with a specific bit depth. The more resolution you have, the more complex and detailed that path becomes.
Okay, so I've turned my 5 and my 3 into these jagged little hiking trails. What's next? Step 2 is radial merge.
Right. And to add them, you don't just stick them end to end. You align them at the starting point, the root of the tree, and you follow both paths. For a while, they might overlap.
But eventually they split because they're different numbers.
And that's where the math happens. The moment they diverge, the operator asks, what's the rotational effort required to bridge these two paths? It calculates the vector sum based on the angular difference the crystal demands.
Rotational effort. So it's almost like it's measuring the strain between the two numbers.
In a way, yes. How hard do you have to turn to get from path A to path B? That effort becomes part of the sum.
Okay, so this implies some really, really weird properties for our new plus sign. The first one that jumped out at me from the notes, it's non-commutative.
Which is just a fancy way of saying order matters.
Right. 5 plus 3 is always 3 plus 5 in our world. But you're telling me here, $1 box plus B might not equal $1 box plus A what?
It might not. If the crystal structure is asymmetric, turning left might be different from turning right. The order you perform the operation can completely change the result.
That is just, it's wild. Imagine if your grocery total changed depending on which item you scanned first.
It's the reality of these kinds of systems. The operator is also scale sensitive. The answer changes depending on your zoom level, your recursion depth.
Because the deeper you zoom, the more jags you see, which means more turns, which changes the rotational effort.
Precisely.
There was one thing in there that grounded me, though. It said this whole thing does become normal addition under one condition.
Yes. If you're moving in a straight line, 0-degree angles.
So kindergarten math is just the special, boring case where you never have to turn?
You got it. Linear addition is just fractal addition with zero angle complexity.
So we have this tool, this box plus theta, but the real aha moment for me was realizing the tool itself is a shapeshifter. The symbol is the same, but the answer changes based on the crystal filter.
That's the heart of conditional collapse theory. The operator is stationary. The environment dictates the outcome.
Let's run through some of the examples from the source because this makes it really concrete. Let's start with a hexagonal crystal.
Okay, so a world structured like a honeycomb. 60-degree symmetries. In this filter, the operator is pretty well behaved. It's isotropic. It acts the same in every direction.
Friendly math, but still not our math.
Nope. Then you have the tetrahedral crystal, a 3D pyramid shape. Suddenly your addition isn't on a flat page anymore. The math literally pops out into 3 dimensions.
But the one that really kind of scared me in a good way was the quasicrystals.
Quasicrystals are amazing. They have symmetries, like 5-fold symmetry, that are impossible in a normal repeating grid. They're aperiodic. They never repeat.
So if the pattern never repeats, and the addition depends on the pattern,
then your addition becomes chaotic, non-repeating. The result of what a dollar box plus B do depends on exactly where in the lattice you perform the calculation.
that blows my mind. An arithmetic problem that's location dependent. Hey, can you come over here? My calculator's giving me a different answer in this corner of the room.
And finally, with a pure fractal lattice, the addition becomes depth dependent. The sum literally evolves as you increase the resolution.
So if I ask, what's 2 plus 2, you have to ask me, in which crystal, at what location, and at what zoom level?
Context is everything. There are no naked numbers in this theory.
All right, let's pivot. We've got this crazy operator. Now, the source material tries to do something really audacious with it. It takes on the Pythagorean theorem.
The Holy Grail. $T plus B2 equals C22.
We all know it. It works for right triangles. But in a jagged, fractal world, do right angles even exist?
Not in the way we think of them. If you zoom in on the corner of a square in this world, it's not a smooth 90-degree turn. So we need a new definition.
And they define a triangle as fractally right if, and this is a quote, the checksum divergence between its legs is minimized. What on earth does that mean?
Think of it as the path of least resistance. In a jagged crystal, there's no perfect 90-degree turn. But there's a turn that is the most stable, the one that fits the crystal's grammar the best. That's minimized divergence.
So we're not looking for perpendicular anymore, we're looking for optimal.
Correct. And they also redefine squaring. It's not just A to BL.
Right.
Remember, a number is a path. Squaring becomes scale 2 fractal encoding. You double the path's length, but you also concatenate its angle sequence.
Concatenate the angle sequence, so you're doubling the history of the turn?
Yes. You're amplifying its complexity, not just its magnitude.
So the new equation looks like the old one, but in a spacesuit, it's a fractally squared, box plus is to dollars fractally squared, equals C to equals C to. E double C to MA2, B2. And this theorem collapses into different truths depending on the crystal filter. The source had this comparison table that was just brilliant.
It really nails the conditional collapse idea. If you use a cubic filter, our normal world, it collapses right back to the classic T dollar plus B2 equals C22. It holds.
Which is a relief. We haven't completely broken the universe. But if you switch to that hexagonal filter...
With 60-degree symmetry, the equation transforms. It becomes D dollars BK2 plus B2 plus 8.
Wait, that looks That looks like the law of cosines.
It's very similar, but normally that's a correction for a non-right triangle. In this hexagonal world, that is their Pythagorean theorem. That extra y plus ab isn't a mistake. It's the natural geometry of their space.
It's the tax the crystal charges you for the angle.
Exactly. And in a tetrahedral filter, the tax changes again. It becomes d$ squared A2 plus B2 fractal 3.
And the chaotic quasi-crystals.
There's no simple equation, no closed form. You have to solve it numerically by finding that minimized checksum. The geometry is too complex to be written down easily.
This is the big takeaway then. The Pythagorean theorem is both true and false at the same time.
It just depends on the crystal condition meaning of what a right angle is. There isn't one single truth.
That is heavy. But let's zoom out because I can hear someone listening and saying, okay, cool thought experiment, but why does this matter? The source connects all of this to cosmology, to a concept they call information curvature.
Right, this is the bridge. We're used to Einstein's idea of space-time being curved by gravity. This theory suggests that angle complexity is like a form of information curvature.
So gravity warps space, and this crystal operator warps the flow of information.
Yes. And think about bit depth again. The source suggests treating bit depth as recursion depth.
Okay, what do you mean?
At a low bit depth, a low zoom level, the universe looks flat. It looks Euclidean. High school math works. But maybe that's just a rendering artifact. Maybe if you crank up the bit depth, you reveal this incredibly fine, non-Euclidean angular structure underneath it all.
So our universe only looks smooth because we're not looking closely enough.
That's the implication. We could be living in an incredibly complex crystal, but our senses are just too low-res to see the jags.
The notes also mention mathematical gravity.
In that model, certain crystal geometries are preferred by the universe because they're more computationally efficient. They minimize that divergence we talked about.
So a right triangle is actually a geodesic.
The shortest path, exactly. But it's the shortest path through information space. So if you measure a giant triangle out in beat space and find the tag dollars plus B2 at 2 doesn't equal 2 dollars.
It doesn't mean your ruler is broken.
It means that space, or rather information itself, is curved right there. It signals the presence of angular structure. It implies matter itself might just be where the math gets really, really complicated.
That is a lot to process. It ties math, physics, and computation into one big, beautiful, weird knot.
The source calls it a fractal Fermat Pythagoras hybrid, a universal scaffold where the rules are built right into the structure of space itself.
Before we wrap, I have to throw out the final provocation from the source. It's a question for you, the listener, to chew on, but it honestly gave me chills.
A black hole question.
Yeah. Could we model a black hole's event horizon as a checksum divergence boundary?
It's a fascinating thought. An event horizon is a physical point of no return. But in this model, what if it's a computational one? A place where the angle complexity goes to infinity.
So the path of a number it can't be resolved anymore.
The recursion depth you'd need to calculate the sum becomes infinite. The universe's computer just crashes.
I love that. A black hole isn't a hole in space. It's a stack overflow error in the cosmic code.
In a manner of speaking, yes. The information stops because the crystal structure is just too complex to compute a path through.
Well, on that note, I think my own CPU is starting to overheat. This has been a really wild ride.
It definitely forces you to reconsider those bedrock truths.
It absolutely does. We hope this deep dive encourages all of you to look at the angles around you just a little differently. Maybe that corner of your room isn't just 90 degrees.
Maybe it's just minimized divergence in a cubic filter. And remember, the symbols might be stationary, but the meaning is always up for grabs.
Thanks for listening. We'll catch you on the next deep dive.